and I will download the recording and put it in files as I did. And today, inshallah, I will remove all the 4 videos that we have under the files, and I will replace them by the recording of this week, today and the next class, inshallah. So let us start. We were here solving unconstrained. It's straightforward, and I think we covered this, right?
Excuse me, doctor.
Yes.
Before we start, I think this week we are supposed to submit the proposal for the project. As per the syllabus.
Schedule, at the end of the 2nd week, right?
Third
week. The end of the 3rd week.
Yes.
So Wednesday, yes. The deadline is Wednesday. So what I want you to do is to what is the approach that we agreed on?
It was general.
You have to propose a problem from your side and tell us what you are going to do on it. This is the term paper, right?
Yes.
So what I need is from you is to go and search the literature for an artificial intelligence technique on your specific problem. You have to have a problem. You have to define a problem of your work, and then you can see the implementation of artificial intelligence techniques on that problem. So then you can reproduce the results first, and then we can contribute in order to have some publication out of it. So try to target transaction papers. You can go and you have IEEE transaction and neural network and fuzzy logic, IEEE transaction evolutionary computation, and you have several Elsevier journals. Try to search the journal publications, and we need some work to strong work, high level work. We don't want just paper and conference, and we try to avoid getting a paper from the conferences. Okay?
Doctor?
Yes, please.
Regarding the proposal, now in this stage still we are not aware which techniques, which method we will use of AI. So is it enough now just to propose the problems and then later on the method we stated?
Of course we can. The method or implementation of the artificial intelligence technique can be adjusted later.
So only we need to state what is our problem now in the proposal, and we just say that we will use one of the AI methods that we will take.
It's okay. At this time, at this stage, you can present, but you have to propose. And what do you want to do with it? Are you going to implement neural network, deep learning, or fuzzy logic, or neurofuzzy, or evolutionary computation? And tell us what are you aiming to do? Okay. And define the problem as an optimization problem or control problem. You need to design a controller and tell us what you want to do with it. ماشي يا ناصر.
ماشي يا دكتور.
Okay. We have Abdullah Muhammad.
Yes, Doctor.
Yes.
When you say use AI techniques, and does this include particle swarm optimization and genetic algorithm?
Yes.
Okay.
Now we defined all the artificial intelligence techniques at the beginning. We have three categories: evolutionary computation. Under this category, you have genetic algorithm, you have swarm intelligence, particle swarm, anti-colony, bee colony, artificial bee colony, and all these techniques are under the evolutionary computation. And the others, of course, physiological neural network. خلاص ماشي. ده الحسن علي. You have a question, Hassan?
Yes, doctor. For the term project, is it an individual project or do we have to stick with our group?
لا, it is a group project.
Okay, okay. Thank you, doctor.
Okay. طيب, we have الفوزان.
Doctor, a quick question here. I think you mentioned that the problem should only address something related to control, or we can have like optimization. يعني for example, if we talk about either equipment by itself, looking into its dynamic and control, or we look into like a load of law and optimization in general.
Either optimization or control. يعني هو control optimization برضه at the end. يعني هو حتى even if it is a control, you want to optimize something, يعني the control parameters also. فهي يعني yes, could be control, could be optimization.
Okay.
And you have to يعني to propose a problem you are familiar with, you experienced it before, you know what are the parameters, the key parameters of the problem, what are the optimized parameters, what are the constraints, what are the objective function if it is optimization. Control, what is the type of control that you will use, what are the parameters or control settings that you want to search for. And you have to be familiar with the problem that you are gonna propose. Okay. So I think we covered all this unconstrained optimization, and we stopped at the solving constrained optimization. In this problem we have, I don't know why this is becoming like a mouse or pointer, not. Anything here. Okay. So when the minimization is constrained, and these constraints, as we mentioned, we have two types of constraints. We have equality constraint. We have inequality constraints. So when the minimization is constrained with equality constraint, we can solve the problem using the method of Lagrange multipliers. With this method, the problem is converted to unconstrained optimization problem. by adding terms to the objective function, by adding the constraints to the objective function. So now we have the objective function, augmented objective function, let us say, and no constraints. So we convert the problem to unconstrained problem using this Lagrange multipliers. The key idea is to modify the constraint optimization problem to be unconstrained problem. The original optimization problem is this is the function or the objective function we need to minimize, and this is the equality constraint. You have several constraints are here, several functions, G1, G2, G3, and so on. So what we will do is to add these constraints to the objective function here by adding terms multiplied by the Lagrange multiplier. So the problem is transferred to unconstrained by multiplying the equality constraint by this lambda. So we augment the problem. Instead of having n variables here or n parameters to be optimized, we add here also the number of parameters equal to the number of constraints. So we expand the problem by introducing these Lagrange multipliers, lambdas, and we augment the objective function now to the augmented Lagrange here. So in this case, we have no constraints and but expanded problem and more variables now in the objective function. But we will apply the same necessary conditions to find the local minima, which is partial L by partial X and the partial L by partial lambda. First derivatives to be 0, partial L by partial xi, x1, x2, x3, x4, and so on. You take the derivative with respect to maybe the constraints also as a function of x. So you have this, and then partial L by partial lambda I. Lambda I will only be repeated or will only appear at G with Gi. So when you get the derivative, it will be Gi. When we say Gi equal to 0, that means that the constraint is satisfied. Implicitly, the constraint is satisfied. This is equality constraints, and the G equal to 0. So when you solve this, that means the constraint is implicitly satisfied. Okay, so you of course you can do some classical way, or you can get x1 as a function of x2, and then you can substitute it here, and then you can keep it only in x1, and then you can get the point where df by dx1 equal to 0, and you can get x1, and then you can get x2, and you can solve it very simple mathematics, using b to eliminate x1. You can have x1 equal to 6 minus 3x2 over 2, and then you can substitute it here, and x1 as a function of x2. So you can have only one variable here, and then you can have df by dx2, and then you can have it equal to 0, and you can define the stationary point, which comes to x2 equal to 1.286. This is a stationary point, and we need to find whether this stationary point is maximum or minimum. So you have to go to second derivative. With this x2, the corresponding x1 is such, but we need to know whether this is, since the stationary point minimum is, so this is x1 and x2. Of course, if you get the second derivative, if this is the first derivative, so the second derivative will be, you have here this is gone. You have here plus 18x2 plus 10x2 يعني 26x2. When you get the derivative, it becomes 26. So 26 means second derivative.
I think it will be 28.
Yes. 28. Yes, 28. Second derivative, b square f by dx is x2 square. This will be 28, which is greater than 0. That means this point is minimum point. Okay? So you can do this. You can use the Lagrange multiplier method. The example is very simple, so we can do we can do this way. It's very simple, but we can also solve using the Lagrange multiplier by adding this constraints to the objective here, and we define here the augmented function. Now we have 3 parameters to be optimized. So fx1, x2 plus lambda times the constraints. The constraints is linear, so we can have partial L over partial x1, x2, and partial L over partial lambda, and this should be equal to 0 for the necessary condition. So we can define this in more general way. So lambda transpose, that means you have several constraints here, and this lambda becomes a vector lambda 1, lambda 2, lambda 3, and so on. So you just expand it here. So when you get the derivative or the gradient of L, so with respect to x, so you get the derivative and also the derivative with respect to lambda, and this derivative is equal to 0. So let us take the same example. This was the constraints. In that example, this was the constraints here. Two x1 plus 3x2 minus 6 equal to 0. So this is the constraints. So we will add it here. So so this is the function, main function, and this is the constraints multiplied by lambda. I have 3 parameters, so derivatives x1, x2, lambda, and these are equal to 0. You have 3 variables, 3 unknowns, 3 equations, 3 unknowns, so you can solve and get x1, x2, and lambda. So as you can see here, implicitly, this constraint is satisfied here. So you can get x1 as a function of lambda and x2 as a function of lambda. And then you can have the just some very simple mathematical manipulation. You can get x1 equal to this, which is the same as before, x2 equal to this value, which is the same as before. So graphically you can interpret this, and the function is elliptical function, and this is the constraints. So to satisfy these constraints and the elliptic function at the same, so this one will be like a tangent here. So this is the solution of this. Okay, another example. Use the Lagrange multiplier method to determine the minimum distance from the origin to this circle. From the origin to xy plane to a circle described by This is the function of the circle. Radius is 5. This is r square, and the center at 8 and 6. So you have here x equal to 8 here, and this is 6. So this is the center of the circle. So what you want to get the minimum distance between the origin and any point here in the circle. So probably this is the minimum. This is the distance. So this distance can be expressed as, and for any point here x, y. So you have x square plus y square. So this is the distance under square root. طبعا ممكن you can say and you can define a distance here as the square root of x square plus y square. And you can even simplify it. You can say d square equal to x square plus y square. So we consider this as the square of the distance, or you can even take it as your objective. If you minimize this one, you minimize also this one. Okay? If you minimize d, you minimize d square. Or if you minimize d square, you minimize d. So it is the same. This should be the constraints of x and y. X and y are governed by the equation of the circle. So you can take minus 25 here, and this is the equality constraints. So this becomes the objective function, x square plus y square. You need to minimize under this condition or this constraints. So the distance from the origin can be described by x square plus y square. It is the square of the distance, but as we mentioned, if you minimize the square, you minimize the value itself. The problem can be formulated as minimize this subject to this constraints. You can add it with the Lagrange multiplier, as you can see here, lambda multiplied this. So we have now 3 parameters, x, y, and lambda. So you can take the 3 derivatives equal to 0 and solve, and then you can get the value. So you have partial L over partial x by partial y and partial L over partial lambda. So you can see here the equations 2x lambda plus 1 and the 2y multiplied by lambda plus 1 equal to 12 lambda and x square and so on. You can see here the equations here are nonlinear equations. And this will be like somehow difficult to solve. It is not similar to the previous one where you have all these equations are linear equation, so you can easily solve. But here are nonlinear equations. But of course, you can start having x as a function of lambda, so 16 lambda over lambda plus 1, y equal to 12 lambda over lambda plus 1 over 2, so 6 lambda over lambda plus 1. And you can substitute x and y here in terms of lambda. So you end up with one equation and one unknown, which is lambda. And you can solve this lambda to and substitute back to get x and y. So eliminate lambda from the first 2 equations. So again, you can do this. You can have y as a function of x. Substitute for y in the third equation. I mean, this is another approach, no problem. And you substitute, if you have y a function of x, you can substitute in the third equation. So you have only x here in this equation, and you can easily solve this. Second order equation, you can have it as such. 25/16x squared minus 25x plus 75 equal to 0. So if you solve this equation, you will end up with two equations. This is two solutions, and this is expected, second order. So we need to now to check which one will give you the minimum value, 4 or 12. So how to do this? How to check whether this is the minimum or maximum, or which one is minimum? So what is the next step, ya Nasr?
Take the second derivative and substitute by the value.
Second derivative here will give you a matrix or just a single equation.
Here we have the single equation, but we have two values for x.
No, I mean a second derivative now. When you get a second derivative means what? Partial square, partial square L by partial x square, right?
x1 square.
We have x, y, z, x, y, and lambda. Okay, x square. And the partial square L by partial x by partial lambda y. And the partial square L by partial x partial lambda. So this is the first row. This is the first row of the Hessian matrix. Am I right? Is it clear or
Yes.
not? Hmm?
Yes, yes.
So you can form the Hessian matrix, and if x equal to 4, then you have y equal to 3, and if x equal to 12, then you have y equal to 9, and lambda equal to -3. So with these values, 4, 3, and 1, so you can go to Hessian matrix and substitute, and you can see the eigenvalues. If they are positive, then it becomes a minimum value. If the eigenvalues are negative, then you have maximum value, or zeros plus minus, then you have inflection point or flat point. So this becomes a minimum when you have, and this becomes maximum. And this is actually the graphically, you can interpret this also. And we have this. If you want to get the minimum distance, this is of x equal to 4, and this one maximum distance of x equal to 12. So you have here x12, you have here x4. So this point gives you the minimum value. This point on the circle gives you the maximum distance to the origin. Okay, is it clear? Any questions? So let us go to inequality constraints and optimization. It is the same. You handle it with the same approach. Practical problems contain inequality as well as equality constraints. Minimize the cost function f subject to equality constraints and inequality constraints. So the Lagrange multiplier is extended to include the inequality constraints by introducing the m-dimensional. You have here number of inequality constraint is m. So you add again m terms here with the vector mu of undetermined quantities. So you add here also some of the terms with this parameter multiplied by the inequality constraints. And here you extend the problem again, but the beauty is that you convert the problem to unconstrained problem. So you will get the derivative, first derivative, partial L by partial x, 1, 2, 3, and so on, partial L by partial lambda, and then partial L by partial mu. And you have here maybe the same example. Use this to determine this is the circle, or yes, you can have it here. Constrained by this, we add here over the last example, we add here some inequality constraints. We need to have 2x plus y is greater than or equal 12. So the point in the circle, we needed to satisfy these constraints. xy, 2x plus y is greater than or equal 12. The minimum distance is obtained by minimizing the distance square. Again, you have this is the objective function that you need to minimize the distance to the origin, x square plus y square. Subject to the point satisfy the circle and also satisfy this inequality constraint. This inequality constraint, this is the equation of, if you have it here, minus 12 equal to 0. So this is a straight line which is here. This is the equality constraint, inequality constraints. So you have here two options, either this point or this point. So the intersection here, the point here satisfy a point on the circle, and also a point is on this boundary, and also with the same point here. But you need to know which one will give you the minimum. It seems we have two points here also. So again, you have if you have the constraint, the quality constraint, and the inequality constraints. So you have extended this function or augmented function here, lambda multiplied by this, mu multiplied by this, and then you can do partial L over lambda, partial L over mu, and you can have these equations now. First derivative equal to 0, so you can solve eliminating and substituting, and then you do this and that, some mathematical manipulation, until you end up with these values. You have this equation, and then you can solve this lambda, then you can go back and substitute for x and y. So you have x and y here equal to 5, 2, and this point and this point. So now the next step is to identify which one gives you the minimum distance, which one is minimum, which one is maximum. So you can go to the second derivative and see. Do you have any question?
Yes, Doctor, I have a question.
Yes, please.
If you can go back to the last example, to the drop, the plot. Here, yes. If you can say that I see the same point we obtained in the previous example, we can obtain it here, since we will meet the constraints.
No, but we have here another constraints.
Yeah, the
This is
constraint,
the problem.
which is meaning that anything in the green region is suitable for this constraint.
Yes. But
And
before the first example, this constraint is not there. Right?
okay.
So without these constraints, the problem is different. لأنه يعني here maybe this point is the nearest one to the origin.
Yes, and it will meet all the constraints. It's in the green region, and also it will be in the circle itself.
I didn't get your point, but let me ask you to clarify this. What is the feasible region here?
The feasible region.
For this problem, we need
Yes.
to minimize the distance under these constraints.
The feasible region will be the point at the green region and in the circle line in the circle itself.
So what do you mean? You mean these 2 points only?
No, all points from in the circle between these 2 points.
Yani here.
Yeah, all these points.
Yes, you are right. Since this is less greater than, طبعا greater than يعني this is the greater than 12 if you take any point وليكن هنا 2 مثلا for x and this is y becomes 1 2 3 4 يبقى 8. So for x2 and 8 y, so 2 and 8, so it is equal to 12. But for example, 2 and 6 means what? 2 and 6. If this is the point here in this region, does it satisfy the condition here?
Yes, then greater.
Doesn't satisfy.
Doesn't satisfy.
If x equal to 2 and y equal to 6, so we are talking about this point. So this doesn't satisfy. So this region is unfeasible region for this constraint. So you are mean now you have the equality constraints. Sorry, the feasible region as this part starting from this point going all over the circle up to this point.
Okay.
So this is the feasible region, right?
Okay, fine, clear.
So this is the feasible region here.
Thank you, it's clear.
Okay. Any question?
Yes, doctor.
Yes.
I have 2 small questions. The first one, is it enough just to substitute the solution pairs in the objective function and see which one is the minimum without going to the Hessian matrix?
Yeah, of course you can do this, yes. But you know, just the Hessian matrix, second derivative, and so on, this will a systematic way.
Yeah, I know it's general. If you have more variables,
course,
you cannot
yes,
tell.
Of course, you have.
The second question is actually, what is the advantage of this Lagrange multiplier? Is there an advantage other than it can be easily solved by hand over the solving packages? In solving packages, you can feed the information without converting it to unconstrained problem.
لا ما هو الباكج بعد كده بيعملها هو يعني الباكج من الداخل هو بيعملها. انت بتدي له الكونسترينتس زي ما هي قدامك بس هو في
Yes.
الاخر هو جوه بيعملها.
Okay.
يعني هو الباكج نفسها بيحولها
Unconstrained.
بيحولها لانكونسترينت، يعني مش انت اللي بتحولها، انما هو اللي بيحولها من الداخل يعني.
Okay. شكرا يا دكتور.
شكرا لك. طيب سالم غانم بليز go ahead. You have a question?
Yes, Professor, regarding the inequality constraint, this is with the symbol greater than for convex problem. So shouldn't we transform it into less than by multiplying the whole thing by minus, so it can fit in the Lagrange formula in here?
Actually, you equate it to zero. يعني you are talking about the boundary here. So if it is greater than or lower than, you have it minus 12 equal to 0. So
Yeah.
you are taking the boundary of this. Okay?
Okay.
So you have it here. So you take the 2x plus y minus 12. So this is the boundary.
Okay. Okay, Professor.
Let me ask you if we have a constraint like this one, v less than or equal this 0.95, so for example, to 1.05. How to handle this? If it is greater than, okay, lower than, okay. But if one variable is greater than or less or equal than, or greater than or and less than at the same time?
I think it will be too constrained.
It will be two constraints. If you take
Yes.
مثلا the less than or equal, this is your standard. Okay. So in this case, you will divide this again. So you will say v less than or equal 1.05, and you convert this to less than or equal 0.95. V is greater than 0.95, so minus v is less than or greater minus 0.95. Okay, so you convert it to two constraints here. Any question?
Yes, Doctor.
Yes, please, Amr Abdul Salam.
Yes, Doctor. Well, what if the problem has two objective functions?
Two objective function?
Yes.
You are talking about multi-objective now.
Yes.
So if you have multi-objective, this is there are two approaches here. مش two approaches أنا طبعا you have several methods actually to handle such a case if you have multiple objectives. But we can classify all these techniques to classical techniques and evolutionary computation approach for handling the multi-objective optimization. So the classical techniques is if you have F1 and you have F2, for example, you need to minimize the cost and maximize the profit or minimize the losses or whatever. The easiest way and the classical way is to aggregate these two functions together. You can define another function which is equal to F1 plus F2. Okay, but of course you have to be careful here. F1 and F2, if you are talking about, for example, and these are the problems of aggregating this, of adding the functions and converting the problem to single objective. Now, instead of two objectives, we convert them to single objective. We can give a weight here, W1, and we can have a weight here, W2, and if we have another function you need to minimize or maximize, So you can add all these weights here, and the summation, W3, summation of Wi equal to 1. So this is equal to, and so on. This weight will reflect you the importance of the function to the decision maker. And if you are very much interested by minimizing the cost, then you have to give here higher weight. This could be مثلا 0.6. This could be 0.2. This could be 0.2 or 0.3, 0.1, and so on. This is one way. This is the classical way to convert the problem to a single objective. But there are a lot of problems associated with this method. The first one is if you have cost and the range of the cost is, for example, $1,000, and at the same time you need to minimize the losses, and these losses will be converted to cost definitely, and this could be مثلا $2. In this case, you can see the respective values, or the if you compare the values here, this is will be most dominant than this one, right? And you cannot compare this when you have it 1,000 here and this is 2. And this will make your problem is very, very weak. Why? لأنه there are these functions are not scaled or are not competitive to each other. And I mean, when you reduce this 1,000 to 990, and this 2 can increase from 2 to 4, right? So instead of 1,000 plus 2, you have now 994. So you assume that you are minimizing, but in this case, it is misleading. And again, you minimize one, and the other objective is going worse and worse. It's not minimizing. You are not searching for the solution that gives you the minimum value of the other function as well. Is it clear?
Yes, Dr. I am with you.
So in this case, you need to normalize. And in order to solve this problem, where you have different functions, you need to normalize the functions itself. And you need to make these functions between 0 and 1. There are a lot of problems associated with the classical techniques, but this is one of them. In addition to the convexity condition and so on, when we are talking about the multi-objective, the things will be much clearer. Okay.
Thank you, Doctor.
Okay. Muhammad Abdul Rahman.
Yes, Professor. What if you don't have any constraints at all? Like we have an objective function and...
But this is the unconstrained problem. So you will implement it df by dx, or partial f of partial x, dx equal to 0. And you get the second derivative, df over dx square, and you can see whether it is minimum or maximum point.
Oh, all right.
So it's straightforward.
Okay.
The problem is with constrained problem. In constrained, we introduce this Lagrange multiplier in order to convert the problem to be unconstrained problem.
All right.
Okay.
Okay.
Okay. So any other question? Otherwise, we will move to The second. Okay. So we will start the evolutionary computation, and what we will do is we will give you a brief introduction to evolutionary algorithms and also the common aspects among the evolutionary algorithms. Evolutionary algorithms could be, as we mentioned earlier, could be genetic, could be swarm intelligence, vertical swarm, or anti-colony, or artificial bee, or even heuristic techniques, simulated annealing, taboo search. All these algorithms have some common aspects. So in all the techniques, you have them. And then we will see the steps of evolutionary algorithms, how it works in order to solve the optimization problem. What is the procedure if you are given an optimization problem, an objective function, and you have the constraints, and then you have the search space defined, the boundary of the constraints, and so on. So what is the procedure in order to reach to the optimal or near optimal solutions? And we will start with the genetic algorithm, which is the mother of all these techniques. Genetic algorithm is maybe the oldest one, and based on the concepts of in genetic algorithm, all these other techniques have been evolved. So in genetic algorithm, in order to improve the solutions to reach to the global optimal solution, we do some operations here. The selection operation, we will discuss it, and how to do crossover, how to interchange information between the individuals or the solutions, and also mutation. This is another operation in genetic algorithm in order to diversify the search. And also the elitism, you may implement this. You can consider some of the solutions as elite solutions. يعني دي النخبة في المجتمع. So these elite solutions are very important. You can, keep them alive with you from iteration or from generation to another. And then we will see the GA computation, the key parameters, the complexity, the computational time, and all these issues related to the genetic algorithm. And this. So generally, optimization techniques can be classified as classical techniques and meta-heuristic techniques. The classical techniques like linear programming, nonlinear programming, mixed integer, gradient, finite elements, Newton-Raphson, and so on. These are the classical techniques. And we have here meta-heuristic techniques. We have population-based techniques. What do we mean by population-based? The technique consider several solutions together, not only one solution, and improve it, like the gradient descent methods or so, but we have here several solutions. We have population of solutions, and these solutions are handled together. And the other meta-heuristic techniques is a trajectory-based techniques. Trajectory-based techniques, you have similar to the classical technique. You have one solution and you want to improve this solution but not based on the gradient descent method. The population-based methods are evolutionary algorithms and the swarm algorithms. So these evolutionary algorithms like the genetic algorithm, differential evolution, programming, differential backtracking, search, etc. And the list here is not exhaustive. And you can particle swarm, artificial bee, bacterial foraging, firefly, gray wolf optimization, and all these methods are under the swarm algorithms. So what we will focus now on the evolutionary algorithms, and then we will see the population algorithms, and we will see also in this, in this course, we will see the trajectory-based methods like taboo search and simulated annealing, and so on. So that's what we will address. Evolutionary computation is in 1960s started by this Reichenberg, and the genetic algorithms specifically invented by John Holland in 1975 in Michigan, and then made popular by John Koza in 1992. Genetic algorithms and also genetic programming. We have also genetic programming, which is different than genetic algorithm. We will see also genetic programming later on. So what is evolution? This is the evolution. You have organisms, animals or plants, produce a number of offspring. And in human being, you have male and female, and then they get married, and then you have some children. Which are these children or offspring? Offspring means children in this context. Almost not entirely like themselves, and you have some, variation between the children, and also between the children and the parents. Nothing typical, or non-typical to other. So you have variation maybe due to mutation. Mutation is a random change. Mutation يعني طفرة بالعربي You have some sudden change happen in the genes, so you have something new or different. You have something different. It could be this change could be positive, it could be negative. This mutation could help in improving the characteristic, or could be detrimental and deteriorate the performance or the characteristic, deteriorate the characteristic. Variation may be due to sexual reproduction. Offspring have some characteristics from each parent, and you have parents, and due to this mating, you have different, children, or different chromosomes, different genes, and so on. Some of these offspring or children may survive to produce offspring of their own and some will not. Actually, some of the طبعا this is usually when we say genetic algorithm or particle swarm or so, these are based on the survival of the fittest. This principle is there, survival of the fittest. When you have two solutions, two children, two solutions, one is good and the other is bad. In terms of the performance, طبعا ده هو solution للبروبلم. You can find one solution is good and one solution is bad. So you can say, let me get rid of this bad solution, and I keep only the best solution. So we have a guided search here. But of course, this is not happening in the human being. And whatever children you have to live with. والله الجاهلية بقى كان زمان ايه يأيدوا البنات okay. So the better adapted offspring are more likely to survive, and the others, of course, will not. Over time, later generations becomes better and better adapted. When you keep the good solutions and you create children from these solutions, and you get better solutions and better solutions over the iterations or generations. Iteration هنا in terms of genetic algorithm we call it generation. لأن genetic algorithm is mimics whatever happen in human being. You have generation after generation after generation. You have here iteration is equivalent to generation in genetic algorithm terminology. So over time, you have generations are becoming better and better. And genetic algorithms use this same process to evolve better solutions. Okay, so the global optimization algorithms based on principles of nature. You have genetic algorithm, you have evolutionary programming, you have particle swarm, you have genetic programming, you have simulated annealing, and the list is very long. And you have every year you can have one new technique is evolved. The researchers are doing their best to propose new techniques. So I think the time is over. So let us stop here and continue next class, inshallah. And if you have any question, please raise your hand. Otherwise, you can leave. Okay, I will stop recording and then